Assalamu alaikum. Welcome to the video presentation of our thesis project, An Efficient Deep Learning Approach to Detect Skin Cancer. My name is Daiyan Khan and I will be walking you through the introduction of our paper. When you think of the two keywords, skin cancer and machine learning, it may not easily come to mind how these two may be related. Before we get into how, I will first give a brief summary of these two keywords. As we know, cancer is the abnormal growth of cells which leads to the formation of tumors, and skin cancer is when these abnormal growths occur on or in the skin. Millions of people in the world are affected by cancer every year, with 1 out of 3 of the skin growths diagnosed to be skin cancer. There are two main forms of skin cancer, melanoma and non-melanoma. As for the second keyword, we will be focusing on one of the subcategories of machine learning, which is deep learning, which is a form of an algorithm which works like a human brain, which is formed of many artificial neural networks which work like the neurons in a human's brain to take input information and give output information according to algorithms and codes set by the programmer. Now that we have a basic idea of skin cancer and deep learning, we shall be looking into how machine learning can be used in the medical field for diagnostic applications. Not all skin growths and lesions are cancerous, and it is not easy to identify whether a skin growth is cancerous or benign without the help of an expert diagnostician. And also, given the fact that the rate of skin cancer around the world is increasing at an alarming rate, will mean that the existence of such an algorithm would make diagnosis easier and much more accessible. To be able to code an algorithm which can automatically detect whether a skin growth is cancerous or not with a high degree of accuracy would be very useful. The purpose of our research paper is to create a deep learning algorithm, in this case using a CNN, a convolutional neural network, that can help identify different types of skin cancer from the images of skin lesions and growths. At the time of recording, there currently exists other machine learning models and algorithms which are able to detect skin cancer from images, but those are based on artificial neural networks, whereas, as mentioned before, our model is based on convolutional neural networks. For the purposes of training artificial neural networks to be able to detect skin cancer from images of skin lesions, there are many publicly available datasets which can be used under Creative Commons licenses for training these said networks. The one we have chosen is the HAM 10,000 dataset, which is available for public use under the Archives of the Harvard Dataverse. This dataset contains 10,015 images of skin lesions and growths. To compare this dataset to other publicly available datasets is the table, as you can see. The images in the dataset are mainly categorized into 7 different categories of skin growths: melanocytic nevi, melanoma, benign keratosis-like lesions, basal cell carcinoma, actinic keratosis and intraepithelial carcinoma, vascular lesions, and dermatofibroma. Of the 7 aforementioned types, only 3 are cancerous: melanoma, basal cell carcinoma, and actinic keratosis and intraepithelial carcinoma. The pie chart on the right shows us the distribution of the 7 categories in the entire dataset, with almost 3/4 of the dataset containing pictures of melanocytic nevi. Other information about each of the images in the dataset includes the age and sex of the patient and the diagnosis type of the image. The diagnosis type is how the diagnosis of each image was recorded, and they are mainly focused into 4 categories: consensus, histopathology, follow-up examinations, and in vivo confocal microscopy. Consensus is for the images in the dataset that did not have any diagnosis, and the diagnosis was provided by the authors of the dataset. Histopathology was the original diagnosis of each image by the doctor who recorded it. Follow-up examinations are self-explanatory, and in vivo confocal microscopy is a form of microscopic imaging. Along with all this, every image has a unique lesion identification ID for the easy access of data in the dataset.
Greetings and Assalamu alaikum. I am Ashfaqul Islam and I am going to be talking about the data pre-processing and model training of our work. Working with any dataset requires a certain amount of pre-processing before it can be fed into the system. For our work, we have used many libraries that can be used with a Python codebase. I will be going over very briefly about each of these libraries that we have used and listed. We have used libraries like NumPy, Matplotlib, Seaborn, Pandas, which are used for things like working on arrays, mathematical functionality, and data visualization. Libraries like PIL and Image Data Generator helps us manipulate, modify, and augment images. PyTorch is an open source machine learning framework that provides functionalities like automatic differentiation, iterability, and common image transformation. sklearn is a machine learning library that features various classification, regression, and clustering algorithms, and it can work with NumPy. sklearn model selection helps us to split arrays or matrices into random train and test subsets, which is useful for any system where training of a model is required. TensorFlow is a free and open source software library for machine learning and artificial intelligence with a particular focus on training and inference of deep neural networks. Keras callbacks can be used to perform actions at various stages of training. Keras layers are the basic building blocks of neural networks in Keras. Keras sequential is appropriate for a plain stack of layers where each layer has exactly one input tensor and one output. Keras models groups layers into an object with training and inference features. For our system to be able to utilize the data present in the dataset, we must read and pre-process the data in certain ways. As mentioned before, this dataset contains a lot more data than just images. It has a CSV file which contains the compiled and compressed RGB data of all the images. We use this to create low resolution counterparts of the images in the dataset, as we wanted to use our model to also be able to work with images that were not very high quality. The dataset also contains a CSV file of metadata of all the images. We use this to identify which image represented what by matching the file name with lesion ID. We then use this information to create a dictionary of images that we later used to modify and augment the images and train the other systems that we used for comparison. We have also labeled the 7 different types of skin growth from 0 to 6 according to the image below. Often, especially large datasets have missing or null values. These have to be filled, and we have searched for and filled in these values with their means. Also, duplicate images might create a bias in the outcome and yield unexpected results. Hence, we have checked for duplicates and used only those images that are unique. From our dataset, we have found that about 4,501 of the images are unique. We're going to be talking about the exploratory data analysis of the metadata of this dataset very briefly. From the first graph, we can see that AKIEC type of skin growths have a lot more occurrence than all the other types of skin growths combined. From the second graph, we can see that histopathology was the most used type of diagnosis method, with the follow-up methodology trailing close by. The third graph shows us that more males are affected by skin growths than females. The fourth graph shows us which region of the body is more prone to having skin growths. The fifth graph shows us the age groups that are mostly affected by skin growths. We can clearly see that the age range of 35 to 50 is the group that is most affected by skin growth. From the sixth graph, we can see the distribution of type of cancer against the distribution of age. And from that, we can see that NV and VASC are the two types of skin growth that affects all age groups. Now I will move on to the model training part of our work. Any system that works with image analysis and processing needs to be able to load and resize images. The original images were of 450 by 600 pixels in resolution. We reshaped these images into 244 by 244 pixels for ResNet, DenseNet, and VGG, as these are the expected image shapes that these models expect. And we use the RGB data to construct 28 by 28 pixel raw resolution images for our model. Any model that needs to be trained with a certain dataset needs to be divided into a training and testing set. We divided our dataset into an 80-20 ratio of training and testing set. This is a typical data science practice. The training dataset is the foundation for any computation that demonstrates how advanced technologies such as neural networks may be used to learn and generate complex outputs. It contains both information and the corresponding expected yield. The training dataset's goal is to provide ground truth data for our calculations. Regardless, the test dataset is used to assess how successfully our computation was produced using the preparation dataset, because the calculation will almost certainly know the normal yield, and we can't just repeat the training dataset in the testing step, which defeats the purpose of evaluating the computation. The training data is further split into two parts in the ratio 80 is to 20. This 20% validation data is used to confirm improvement in training. Your neural network is overfitted if the accuracy of the training dataset improves while the accuracy of the validation dataset remains constant or diminishes, in which case you should stop training and re-evaluate your model building. However, while normalizing, one must make sure to do so without distorting differences in quality scores. It is only necessary when features have a wide range of values, like in our case. Data augmentation can be described as the process of artificial and varied expansion of data to avoid overfitting and stop our model from learning irregular patterns. These expansions are done by varying existing data in certain ways and multiplying certain data by a scale factor. In our case, we have rescaled the images from a pixel value range of 0 to 255 to a range of 0 to 1. We have rotated the images randomly within a 0 to 10-degree rotation. We have also shifted the images both vertically and horizontally, as realistically images fed into the model will not always be centered. We have also sheared the images randomly up to 20%, as images will not always be captured from a perfectly horizontal position.
Assalamu alaikum everyone. My name is Rakeen Ashraf Chowdhury, and now I will be discussing about model building and evaluation. What is CNN? Convolutional Neural Network, or CNN, is a neural network which follows artificial neural network, mostly used for images, audio, etc. Artificial neural network uses one-dimensional data. CNN applies different types of convolution, striding, and pooling to three-dimensional data, for example images, and transforms it to be able to fit into a neural network, that is, one-dimensional data. Then it feeds to the neural network and performs the operations in order to get the desired output. The images are basically matrices. Convolution is applied to the images, and the 2D or 3D data is flattened to 1D data, and then it is fed to the neural networks. Feeding a three-dimensional data to a neural network was not as easy before, until CNN made it easier by the usage of convolution and flattening. Model building and evaluation using ResNet 50. What is ResNet 50? Residual neural network, or ResNet, is a kind of an artificial neural network that was introduced in 2015. It builds on constructs known from pyramidal cells in the cerebral cortex. Skip connections or shortcuts are used by residual neural networks to jump past some layers. The majority ResNet models use double or triple layer skips with nonlinearities such as rectified linear unit and batch normalization in between. The ResNet network employs a VGG19 inspired 34-layer plane network architecture, after which the shortcut connection is added. As seen in the diagram, these shortcut connections change the design into the residual network. Model building and evaluation using DenseNet 121. What is DenseNet? Dense convolutional network, also known as DenseNet, is a convolutional neural network in which each layer is linked to all of the levels below it. This CNN uses dense blocks to link all layers directly to each other, resulting in dense connections between layers. Aside from better parameter efficiency, DenseNet also allows networks to be trained more effectively. They can provide better gradients and better flow of information across the network. In the figure, we can see that these 32 new feature maps are added to the preceding volume by each layer. This is the full schematic representation of DenseNet 121. Model building and evaluation using VGG11. What is VGG11? A group of students formed a group called Visual Geometry Group who invented VGGNet. This model has been pre-trained on a dataset and has weights that represent the dataset's attributes. If we look into the convolutional layers, VGG11 contains three nodes that are fully linked. The upper two completely linked channels each have 4096 channels, as seen in the picture here. These are the 11 layers of VGG11. Our CNN model was built using Keras Sequential API and we trained it on our dataset. This is the architecture of our model. We have also used three other pre-trained models such as ResNet 50, DenseNet 121, and VGG11. For our model, we got an accuracy of an average of 97% of both training and validation accuracy, considering only the last 5 epochs, whereas ResNet had a validation accuracy of 87%, DenseNet had a validation accuracy of 89%, and VGG11 had a validation accuracy of only 83%. If we look at the accuracy and training and validation phase of the models, we can see that our model yielded pretty accurate results compared to the other three CNN models. Lastly, if we take a look at the F1 scores of the three models, we can see that our model has been given an F1 score of 0.98, whereas the other models were given 0.88, 0.91, and 0.87 respectively. Other matrices are presented on our paper. The reason for such a high level of accuracy is because we trained the entire model on our own data. In the case of pre-trained models, the weight distribution has not been made for our purpose. They are made for a different purpose, but we are using it to our own use. Therefore, it does not represent our scenario perfectly. It is not wholly meant to work for our case. On the other three models, the accuracy is alright, but not as accurate as our own model. Since the models were not trained on cancerous and non-cancerous images, therefore it does not perform spectacularly well when classified between the cancerous and non-cancerous images, hence the poor validation accuracy. So that was the end of our thesis presentation. Hope you all have a good day. Assalamu alaikum.